Yoeri van den Burgt. Welcome, Yoeri.
Hello.
Hello. So Yoeri van den Burgt obtained his PhD degree at Eindhoven University of Technology in 2014. He then worked at a high-tech startup in Switzerland, after which he obtained a postdoctoral fellowship at the Department of Material Sciences and Engineering at Stanford University. At the end of 2016, he returned to Eindhoven as an assistant professor, where he currently leads the Neuromorphic Engineering group. He has also been a visiting professor at the University of Cambridge. And he will give us now a talk about organic neuromorphic materials for adaptive biointerfaces. So Yoeri, the stage is yours.
Yeah, thank you. Thank you very much for introducing me. Also, thank you very much for inviting me to this great symposium. It's actually very fun to see all these different perspectives on the transhuman vision. I renamed my title a little bit to be a little bit more in a discussion form. So I'm a material scientist, and we work on materials to do things like building a brain on a chip and biohybrid systems. In a more detailed word, that would be organic neuromorphic systems. And I try to highlight in this talk a little bit what the vision is of these materials and why we work on them. And I would like to start actually by introducing a very familiar topic to everyone, I guess, by now, is artificial intelligence. And previous speakers already touched upon it. But AI nowadays is basically adapting computer systems to emulate sort of brain-like functionality. So they can make systems, machine learning, that can actually be trained to improve itself with experience. So you can feed it information and it learns and it becomes better. Now you know a couple of examples of very recent applications like face recognition on your phone to unlock it. That has been recently introduced, but there's also image recognition on tools like health diagnostics. But you know, image recognition can also be more futuristically seen in this example here, in this picture that I found somewhere, where it can be used in companies or even governments that can recognize different people instantly. And there's also some ethical discussion that we can talk about here. Another nice example of this, and that's the last example I show, is self-driving cars. Although they have still been a promising technology for more than a decade now, it's still something that is being developed very well. And you need systems that can train and that can learn from data that they find online, that they can find, sorry, not online, while driving from other people on the road. Now, in a nutshell, most AI systems are based on algorithms called neural networks. And on this slide, there's a couple of them, there's many more, and I won't go into details. But the important thing to understand here is that these networks rely actually on the modification of the connections between these layers of these dots here. So the hidden neurons and the synapses of this neural network. And there's actually, AI is not actually very new. In fact, it's been around for decades. And there's two reasons that this time it is actually increasing much more rapidly and is here to stay. The first is the vast amount of big data that is available nowadays to train the networks. And this is just an example of a lot of images. But again, these systems can only become better by learning, by training from examples, such as shown in this picture here. And the vast amount of images that we are all uploading every day onto the internet nowadays. For instance, neural networks you can very easily train with labeled data that you can actually get from a software system called, or software database called ImageNet. And it's important that these are labeled, otherwise the system cannot be trained. Now, the second change was actually the development of graphical processing units. And they have been used in dedicated neural networks and greatly improved the efficiency and speed in these neural networks. And if you remember that all these networks have all these different connections that need to be updated, you need to do this in parallel. And the idea here is that GPUs have many cores in parallel, so they can do many calculations in parallel. That's why they become so important for these AI applications. And this is just a simple graph. It's relatively old by now, but it highlights the implementation of GPUs for AI, where you can see that near the end, the potential of these GPUs has been proven by outperforming humans actually in this ImageNet example of images that I just showed you. And in 2016, actually, a computer won against a human player in this Google DeepMind. Google DeepMind won from a human in this game of Go, and Go is actually a very complicated game that you cannot before the game tell all the different moves that you can take. So it's really something that the computer had learned. So it's not done by remembering, it's just by playing against itself and improving on that. However, that took a lot of computing power. And there's some calculations to compare between the human and this data center here, this computing center here. But it's about 10,000 times more energy that is used. Now, this is where material scientists come in. This parallelization of these neural networks was also introduced by so-called memristor arrays. This is just a SEM image of a memristor array, where the devices actually have a memory component in the center of these crosses, and that can actually be modified depending on the history of the device, how it was operated. So you have some memory part fulfilling the memory of the computing part. Now this is actually very similar to the brain, and this is where the brain part comes in, where the brain, and I'm not a neuroscientist, so I'm glad that the previous speaker actually introduced this topic very well, but the brain consists of neurons that are processing units in the brain, and they are connected via these synapses here, these red dots in the center. Now these synapses can actually change their conduction, their resistance to each other, and that depends on the activity of those neurons that are involved in that synapse. Now, if neurons talk to each other very often, those synapses become stronger, and you can actually memorize or get a better connection between those neurons. So you memorize, you learn something. But as a result, the brain activates memorize something that is activated very often, and it can do this actually by physically moving the two sides of the synapse together. Now, this is exactly what we have done in a device based on organic materials. So we have a plastic organic material, and the resistance of the bottom polymer and that you see in this schematic here, the blue part, can actually be tuned by moving in ions from the top part. Now, we can thus perform the memory part of neuromorphic device. We can train it by learning from inputs. And this is actually, if you look at the synapse compared to our device, it's kind of similar. So we have mixed electronic ionic connectivity of a polymer. We can non-volatilely electrochemically dope this, and we can actually show short and long-term potentiation. Now, the first devices look a little bit like this. So large flexible ones or smaller arrays. But obviously, we want to go to more flexible, larger arrays. And this is an organic memory array from Professor Someya's group in Japan. And the nice thing about this is you can already see this is also very interesting to be able to interface with the body because it's flexible. You clearly see that this might be connected well. And this is where we touch upon a new research field. As on the biological side, we have this field called bioelectronics, where we interface devices and materials with the body to monitor and control or restore functionality. Now, as an example, we have actually used our organic device in combination with as real synapse, with real cells. So we have made a biohybrid device that can actually learn, and this is the only real graph I show you in our slide, where we have this neuron that actually talks to our organic polymer in the blue there, and by releasing neurotransmitters, it can actually change the conduction of our organic device permanently. So you see a short-term modulation from the synapse and a long-term modulation here. There's a difference between the conduction between the starting and the end. So what it actually does, it memorizes, not only measures, but also memorizes the history of pulses from this neuron. So you have an adaptive interface between a neuron and an organic artificial device. And this is where we can think about applications like local control, trainable prosthetics. You can imagine that you can controlling these prosthetics uses a lot of computing power. And if we have these adaptive interfaces between our nerve cells that control the hand and the prosthetic itself, we can actually improve this connection and let, for each connection, for each person be adapted personally. So you have a more personalized connection between those two. In the end, you can think of other things. I just highlight a couple here where you have some adaptive drug control depending on the need of if you have a seizure or you have some other need of drug control, you can do that locally without a computer controller because the devices can be adapted locally. So we have here the adaptive prosthetics, or even thinking about interfacing those electrochemical adaptive devices with the spinal cord that might be broken. So you combine artificial intelligence using materials with our body. I'm a little bit over time, so these are just my acknowledgements, and thank you very much for having me, and I'm happy to take any questions.
Okay, thank you very much for your talk. Really interesting. So we have a question that's kind of related to what you said. You can control like a bionic arm or something, but a little bit to a different direction. Would it be possible to use this technology in the future, maybe to transfer memories to a machine or something to continue on living if the human body fails?
I think that's a great question. So in the end, it has to be something like a material that is more related, more suitable to functions like the brain. So if you want to copy the brain somehow you cannot just measure the activity with the gold electrodes. You have to also do something with your neurotransmitters. You have to do some, brains actually talk with ionic currents going through the synapses. It's not electrical currents. There's some electricity, but it's not. So you really want to have something that is more related to the brain itself. So yeah, definitely, it's going to be very complicated. But I foresee that it has to do something with a material. You have to do it with a material that is more related to how the processes in the brain work too. So yeah. Who knows?
Nice. This is really exciting. And we have another question from the chat. How is the stability of I can't read it. Can you?
Chemicals.
Yeah, P.PSS in biological environments.
Yeah. So Nigel would expect some polymer degradation over time, especially in P.dots is also used OPV, which tend to degrade. I don't fully understand this question, but hopefully you do.
Yes, I do. So P.PSS is indeed used in solar cells as an interface layer. So what we have to do with P.dot is to add a crosslinker. So you add some crosslinker during the spin coding, and then it's highly stable. So there are actually interface devices based on P.PSS that are currently in use and approved by the FDA in the United States, and they can be implemented in long-term. Colleagues of mine work on these long-term implants in mouse, in rats, in other larger animals, and there's no degradation as long as you have this crosslinker. So you're right, for OPVs they don't use it, and then it degrades.
Okay, thank you. Here's another interesting question from the chat from Ewout. He's asking, instead of moving a limb, would it be also possible to connect the biological chip to the internet and serve the internet with your brain?
Yeah, so for sure, we're doing the fundamental work of the materials, but if you look at Elon Musk's Neuralink project, which is basically what he claims in those kind of things, right? You can do everything with thinking about it and moving things and surfing the internet. So their devices are just probes that measure activity of cells using conventional electrodes. So our devices are not only measuring but storing. So in principle, I would say it becomes easier to do those kind of things because you can measure not only activity but also, if you're happy, you have some other neurotransmitters that are released that you can actually sense too. So you can do more with emotions than just with activity. And I think it's definitely a long shot in the far future. But if you connect somehow correctly the brain to our chip, then sure, why not?
Yeah, nice. Do you think this would make the exams obsolete?
So if you can do it bidirectionally, so you can also copy back something, yeah, then for sure, yeah. But maybe exams will become even more difficult because it turns out you have to find somewhere in your mind where the answer was, right?
Yeah. Okay. Thank you. And there is another question from the chat from Reynaud. What is missing in the materials department that make current implementation so difficult?
Yeah, so this is, that's a very good point. And it touches upon the difficulty of research nowadays, which is actually that it's becoming more and more multidisciplinary. So, we can make materials, but we need anesthesiologists, we need surgeons to put those things in brains. We have to work together with huge consortiums. You saw in previous speaker someone who actually has those huge consortiums. You see all the names on that list. So for me, that is actually the biggest bottleneck: finding the right and the right amount of money and people to work together in bigger consortiums on these things. At the same time, materials devices like these are very fundamental, and they actually also need optimization and scalability issues to be overcome. But that's more a technological problem than a fundamental one.
Okay. Okay, thank you. And the last question from Mark. And can a person restore emotions and facial expressions in Parkinson's disease?
I'm not an expert, honestly, on that disease, and also not on the issues. What I do know from my colleagues who work on bioelectronics is you have these implants in people who have Parkinson, and when it's basically a bioelectronic device that gives pulses at a certain region, and when they switch it on, actually they lose all the tremors and they can just function normally. So there might actually be some solution also for facial expressions or emotions if you don't have these tremors anymore. But I'm not an expert. I would hope so.
Yeah, let's hope so indeed. But yeah, thank you very much for your answers, for your amazing talk. We'll continue during the panel discussion.
Thanks for having me.
Thank you. And now